This week in lab, you're going to look at rotational motion. As such, your objective is going to be to measure the moment of inertia for a disc, a bar, a hoop, and an irregular object that we just cut out in the wood shop. So let's talk about how we're going to do this. Let's talk. If you exert a force a distance away from an object's center of rotation, you will cause this object to rotate. And we call this force exerted a distance from the center of the object a torque. And is analogous to Newton's second law, we get the torque equals the moment of inertia times alpha. Where alpha, right here, is your angular acceleration. That's how fast this thing spins. Angular would be radians per second squared. I is the moment of inertia. Different shapes are harder to get spinning or stop spinning. And then torque, which we've already discussed. So let's talk about what this looks like in your lab. So in this lab, you've got a disc right here. And on the bottom of the disc, there is this aluminum pulley. And what I want you to note is that the rope is going to be tied to this pulley. And as the pulley spins, this is in spindle motion, as the pulley spins, if we watch this, see the dots right here? Watch this dot on the pulley, this dot here. As the pulley rotates, you will see that it has the same angular acceleration as the big disc. So you are going to hang a mass on this pulley. It is going to pull, as it falls, pull this disc, and it's going to spin them both. Your disc is going to be upside down. I just wanted to show you that this pulley is right here. So the thing to note is that alpha for the pulley equals alpha for the big disc. All right. So this is a view of your apparatus from the side. Very important. This is the pulley. Make sure that this pulley string is straight. You'll have to line it up. You'll also need to make sure that the table's level. That way you're not pulling at any weird angles. Your mass goes here. Please don't use a fish in lab unless you are refrigerating it. And it will drop, which will exert a torque, and then cause the disc to rotate. Now in this lab, we're actually ignoring the moment of inertia for this aluminum pulley. That's because it's very close. And as you saw from class, this depends on, or moment of inertia depends on radius squared, so we're not going to mess with it. Right. Also very important, as we mentioned, there are three. You want to use the pulley in the middle. This means you're going to have to look at it and make sure that it's actually wrapping around this particular one. Its radius for the center pulley is approximately 2 centimeters, but as this is physics lab, you are always going to measure. And lucky for you, we've provided calipers, so not only are you going to measure it, you're going to measure it very well. So in part A, you're going to drop the mass, we're going to let it go, it's going to start to accelerate, and it's going to spin and spin and spin. And oh, you see that snag? And then it fell off the pulley? Well, that's bad. You can stop it before it does that. But in the first part, you are going to find the actual torque. There's this nasty little thing called friction, and you can't really ignore it. But what we can do is if we solve for torque using the moment of inertia for the disk that we measured, and this is 1/2 mr squared, where r is the radius of the disk and m is its mass. And if you measure the angular acceleration, which we're actually going to talk about this, how you can convert the velocity tangential, because notice, this is your pulley. All it records is the speed that this pulley is moving, a linear speed, a tangential velocity. But we want alpha, so let's talk about how we're going to do that. Now, so you don't have to do this by hand, we're going to use our good friend Logger Pro to the rescue. So if you'll notice, this is a velocity time graph, and if you take tangential velocity over time, this equals tangential acceleration, which is the slope of this graph. Now, like in the last lab, you only want to select the good parts. In other case, well, you can tell this part looks like a nice straight line. And this is where it fell off, so don't do that. And this is where it's coming back up. So we're only going to select this part right here and get the slope. Now, it's important to note that the A tangential for, I'm going to call the pulley 1, equals the tangential acceleration for the pulley on the disc. All right, that's because the rope is leaving this pulley at the same rate it's leaving the pulley on the disc. And then we can say that tangential acceleration equals r alpha. In this case, this r is going to be the pulley on the disc because, well, we want to know the angular acceleration of the big disc. And as we mentioned earlier, the acceleration for the pulley on the disc, that is hard to read. Okay, the pulley on the disc is the same as the angular acceleration for the disc. And that's how you're going to get your alphas in every single experiment. So what other parts are there? Well, I'm glad you asked. You're at least thinking to yourself. Maybe. Okay, so in part B, you are going to look at the elusive moment of inertia for this bar. And as you can see, same thing happens. It starts spinning. We drop the mass, and it starts spinning. In part C, you will put the disc on here, and the disc has little holes in it, like right here and here. They mount to little protrusions on the disc so that it doesn't fly off, because that's dangerous, and we don't want that. And then the disc will spin. And then in part D, you're probably wondering why there's this big question mark. That's because this is the moment of inertia of a mystery shape. Who knows? Whatever we decide to find in woodshop, or whatever we put on the rotational apparatus that day. So now let's talk about what you can do. Now, very important, in parts B, C, and D, you are finding the moment of inertia. And you know, moment of inertia is equal to torque over alpha. And this torque is from part A. It is the torque from part A every single time. That's why we had part A, so you could find the torque. And the alpha is the one that you will pull off Logger Pro. So now that you've got this, you know there's some uncertainty in torque and T actual. Again, this is always the torque from part A, always. And you did this 2 or 3 times, so you've got uncertainty. You get uncertainty in alpha. Why? Because you measure it multiple times. So your uncertainty here is going to be I equals torque over alpha, like we said. Oh, look, you are dividing. What does this mean you do? It means you add percents. All right? So you know the percent torque is off, you know the percent alpha is off, you can find the percent that this is off. That's not the only thing that could have gone wrong, though. Your theoretical values could also be off. So well, what'd you measure? You measured R, you measured the mass. I didn't write that down, so maybe you do that yourself. You'll have uncertainties in R's. And then from this, you'll propagate this error, and you'll get a range for your theoretical value. You get a range for your experimental value, and hopefully the true value for the moment of inertia of those objects is going to be in that overlap. And then you can explain to me why they don't exactly line up. So in short, part A, you are finding the actual torque. In parts B through D, you are measuring moment of inertias using torque over alpha equals moment of inertia. And then you are going to compare your theoretical moment of inertias with your actual moment of inertias. You won't be able to do this on the funny shape. Well, you might be able to, but that's not something I'm going to make you do because it is a funny shape. If you have any questions, just let us know, and I will see you in lab.